All right, so here we have problem number 58. I wasn't going to do this problem on a video, or I didn't do it in class, because we talked about the fact that I had already done a problem like this and showed you the technique at the beginning of the Smart Notes, which are also posted on Blackboard. But to see it on a video might be helpful. All right, so here's the situation. We have a hiker who is hanging from a rope, or hanging from one rope that's suspended from two other ropes, okay? So he has a certain weight that's acting downward, and you'll see the rest of that later. All right, so his weight is acting downward, and so we have two different dotted lines showing the direction of the forces. So we got a force that's acting this way, that's the tension in the left-hand rope, and a force that's acting this way, that's the tension in the right-hand rope. All right, so we'll call the blue one on the left T1, and we'll call the green one on the right T2. All right, so T2. All right, so now here's the thing. They have given us angles from the vertical. Here 65 is measured from the vertical, and here 80 degrees is measured from the vertical as well. I think that our approach to this problem, so that we can be more consistent with the way we've done things before, it would be helpful for us to redefine those angles in terms of measurements from the horizontal. So what I'm going to do is stick a horizontal in here, and we're going to say that instead of calling this angle over here 65, we're going to say theta, we're going to call 25 degrees, okay? And then we're going to call phi over here 10 degrees, the complement of 80, okay? So 10, 80, and then 25, 65, those are complements to one another. So let's redefine everything in terms of those variables, all right? So now we have 535 newtons, and I'll just slide that down later, is our weight acting downward. So we know two things. We know that the y component of the blue force plus the x component of, or the y component of the green force, y component of blue plus y component of x, have to equal the weight. All right, because we know that the net force is equal to 0. That should be a big thing we have up at the top. Net force is equal to 0. Okay, that means that net force in the x direction is 0 and net force in the y direction. They're both equal to 0. So those two add up, these two here add up to this, so that they're equal and balanced. And the more important thing is, well, equally important, is that the x components are also equal, right? Their components have to be equal to each other. mg has no component in the x direction. So the only things acting in the x direction are T2 and T1. Specifically, they're x components, and those x components have to be balanced. All right, so those are the things we're going to take into account as we go towards solving this problem. All right, so what do we have here? I don't know why I have that. Oh, we're calling this the positive x direction. It doesn't look like that's what that says, but it does. All right, so what we first got to do is, I think what helps to start with, is to look at what's going on in the x direction. All right, we know we only have two forces acting in the x direction. We have two variables. If we could get one of these in terms of the other, in terms of what's going on in the x direction, we can then substitute that into what's going on in the y direction and then end up with only one variable. All right, so let's look over here on the right, and we have net force in the x direction is equal to 0. We know that's true, because if the total net force is equal to 0, then the net force in any direction is equal to 0. Net force in the x direction is also equal to T2x, the x component of T2, minus the x component of T1. All right, because this is pointing in the negative direction, that's why the negative sign. Putting those together, we get that T2x minus T1x is equal to 0. All right, and then moving on a little bit further, we could see that T2x is equal to T1x, right? If you started right here, that's fine. You just sort of intuitively see that their x components have to be balanced. The two-equation strategy can help you get here if you don't know that that's true, but if you know that that's true, that's a fine place to start. All right, as a result of that, we know that T2 cosine, I wrote these backwards, T2 cosine phi, right, because phi goes with T2, here's phi, all right, is equal to T1 cosine theta. All right, because this is the x component of T2, this is the x component of T1. All right, so now, putting those two things together, we can easily see that, I wrote this upside down last time, we can easily see just by simple algebraic manipulation, that T2 is equal to T1 cosine theta over cosine phi. Okay? We just divided each side by cosine phi. Now, what good does that do us? Well, that tells us in the y equation, the y, all the stuff that's going on in the y direction, that where we have T2, we could substitute T1 cosine theta over cosine phi. And that's exactly what we're going to do. All right? So, let's go back and see what's going on in the y direction. We know that the net force in the y direction is equal to 0, just like it is in the x direction, over here, just like it is up here. That's true. If that's true, then no matter how you draw a line through, the net force or components of those forces have to add up to 0 along that line. Net force is equal to 0 in the y direction. Now, here are the forces that are acting in the y direction. T1 has a y component, positive, plus T2y, a positive component of T2, has got to be equal to the negative component of mg, right? So this plus this minus this are going to equal to 0, as we see right here. All right? That's just the two-equation strategy again. Again, just like if you did it over here, you might be able to just start here and say that T1y plus T2y is equal to mg. Easy enough. Looking up here, that's how we drew those to be the right size. So we know that the y component of T1 plus the y component of T2 is equal to mg. This is where the information that we got before is going to become useful, okay? And that is that we solved for T2 in terms of T1. All right, over here, T2 is equal to T1 cosine theta over cosine phi. So now instead of writing T2y, we're going to make the substitution. Actually, let's first make things a little easier, and we'll say T1 sine theta plus T2 sine phi are equal to mg. Now we're going to take this substitution and replace T2 with T1 cosine theta over cosine phi. So T1 sine theta plus T1 cosine theta over cosine phi still times sine theta, sine phi, sorry, equal mg. Now we can simplify this and say T1 times the quantity sine theta plus cosine theta tan phi, right? Because we got sine phi over cosine phi is equal to mg. I just factored out the T1 from each of these two expressions. Now moving along a little bit farther, pretty easy to see that T1 is equal to mg over the quantity sine theta plus cosine theta tan phi. All right. Now, with the numbers that we were given, remember we took the complements of the angles that were given so that we could measure things from the horizontal and have our more familiar orientation of cosine being associated with x and sine with y. So T1 is equal to mg, 535 newtons, over sine of theta was the complement of 65, so 25 degrees, plus the cosine of 25 degrees, times the tangent of 10 degrees. That was the complement of the 80 that was given. Okay, so now all we have to do is plug and chug this a little bit. And crunching out all these numbers, we get that T1 is equal to 919 newtons. All right, so that's how we get the number. Notice how much algebra we did before we ever even plugged in numbers. Now, just a quick dimensional analysis, we have newtons, and all these things down here are trig functions, dimensionless. So we're going to end up with newtons divided by nothing, so we get newtons. So T1 is equal to 919 newtons. And now we just have a quick job of saying T2 is equal to T1, and go back up here and see what that substitution was. T1 cosine theta over cosine phi. So T1 cosine theta, 25 degrees, over cosine phi, cosine of 10 degrees, gives us a new number, 845 newtons. Okay? So just down here to make it a little cleaner, T2 equals 845 newtons. All right, so that is how you do the hanging mass problem. Solve for, in general, solve for what's going on in the x direction, get one of them in terms of the other, then take that substitution and put it into what's going on in the y direction. Okay? Go back and look at the video and look at the flow of information, how we solve that. That's a good one to know how to do with the test coming up tomorrow. All right, that was number 58.